In this video, we're going to look at electric potential energy and electric potential. And if you think of a basketball as being lifted up in the air from position B to position A, it has increased its mechanical potential energy. Well, you can do the same kind of thing with charges. This positive charge here has been pushed from position B to position A towards this line of positive charges. It was hard. It was difficult to do it. You needed a force to push it there. And the electric potential energy of this charge now is increased as you moved it closer to these upper blue charges. The work that we did in lifting this ball up equals the change in potential energy. Well, the same thing holds true for electric charges. The work we do in moving this charge from position B to position A is equal to the change in electric potential energy. That's final minus initial. Now we're going to look at something called electric potential difference. Not electric potential energy, but it's called electric potential. And this is very important in terms of how strong an electric field is. The definition for electric potential is V. The electric potential V at a given point is the electric potential energy, EPE, of a small test charge, Q sub naught, situated at that point, divided by the charge itself. So the equation of this V here is electric potential, that's volts actually, equals electric potential energy divided by the test charge, Q sub 0. So it really comes out to be joules per coulomb of charge, which ends up being volts. The electric potential difference is just that. It's the difference in potential between 2 points. So if we look at this in terms of an equation, we have the final position minus the initial position. So that's our electric potential difference. It equals the electric potential energy at point B over Q sub naught minus electric potential energy at point A divided by Q sub naught, which we recognize as being the work being accomplished all over Q sub naught. And the reason why it's negative work is because it's the final minus initial gives us a negative value. So if we write this in a different form, we say the change in potential equals the change in electric potential energy divided by the charge, which equals the work divided by the charge, the negative work divided by the charge. Let's say we have a situation here where we have a charge as it moves from A to B in this case. We want to see what the work done by the electric force as the test charge moves from A to B. And you'll notice that it's a positive 5 times 10 to the negative 5th joules. That work is positive because the force from the electric field is down. The displacement that it's moving in is down. They're both in the same direction, so that's why it's positive work. The charge itself is 2 times 10 to the negative 6 coulombs. So let's say we want to find the electric potential difference. We want to find the difference in electric potential energy of the charge between these points. We can go ahead and just say it's equal to the negative work being done. The change in the electric potential energy equals negative 5 times 10 to the negative 5th joules. The work was positive because our force was down and our charge and our displacement was down. But the change in electric potential energy is negative because the electric potential energy actually decreased. It became lesser. Now, if we want to determine the potential difference between those 2 points, what we can do is use the equation. Potential difference equals the change in electric potential energy over Q sub naught. So that's really just the work, the negative work done, which is negative 5 times 10 to the negative 5th joules divided by the charge itself, which gives us a value of negative 25 volts. So what I want to address is, why do we tend to talk about potential difference instead of potential? Well, if you start off with a lower potential and you go up towards higher potential, we see a difference in potential. Or if we start at a higher and we go down to lower, we see a difference in potential. I don't care what potential we're at right now. I want to see what the difference is in potential. And that tells me how strong the electric field is, which tells me how much force is acting on the charge. If I know just what the potential at one point is, that doesn't tell me how strong the electric field is at all. It's also important to realize that a positive charge will accelerate from a region of higher electric potential towards a region of lower electric potential. So a positive charge will go to this lower electric potential area, which is made up of negative charges. And a negative charge will do the opposite. It will accelerate from a region of lower potential towards a region of higher potential where the more positive charges are. So negative charges go towards areas of higher potential. Another type of question we want to be able to answer is, what is the speed of a particle when it reaches point B? Okay, so we're going to look at this information here on this picture. It says a particle has a mass of 1.8 times 10 to the negative fifth kilograms and a positive charge of 3 times 10 to the negative fifth coulombs. It is released from rest at point A and accelerates horizontally until it reaches point B. The only force acting on the particle is an electric force, and the electric potential at A is 25 volts greater than that at B. So we know the potential difference between those 2 points, and we know that's why this charge is accelerating, is because of this potential difference. What is the speed VB of the particle when it reaches point B? So what we're going to do is we're going to think of the idea of conservation of energy. Potential energy is converting into kinetic energy. So when we go ahead and think of that, we say, well, initially we have both potential energy and kinetic energy. We have its initial energy at point A is 0 meters per second. So that right there is going to go away. That 1/2 mVA squared is going to go away. This potential energy that it has is equal to the potential difference times the charge. And that right there, that potential energy will convert into kinetic energy. So we go ahead and look at that equation, rearrange it, and we plug in our values, and we end up with 9.1 meters per second. The last section we're going to look at is electric potential difference created by point charges. Now the equation for that, the potential of a point charge is V equals KQ over R. And so there's our equation. The potential of a point charge is V equals KQ over R. Potential difference, we know, is work divided by charge, negative work divided by charge. And if we go ahead and plug in also that it's equal to KQ over R minus KQ over R, our potential difference, we can find out that, and we multiply through by Q sub naught, we can rearrange this to be work done to move a charged particle is equal to KQQ over R minus KQQ all over R. That work can also be thought of as the potential energy between the charges. So this work will equal a change in potential energy. So this KQQ over R is the potential energy equation for point charges.